that you've all had Circuits 1. It's not really a prereq to this course, okay? But I'm assuming that you're at a point where you've already had it, okay? If not, then I would suppose at the latest you would be in it now, okay? But I doubt that. I bet most of you already had it, okay? And I think it's helpful to review anyway. So first off, we have to review the basic elements of circuits, RLC, right? Resistors, inductors, capacitors, okay? So let's talk about the resistor, okay? The resistor has an important property. It relates the voltage to the current. You can write it lots of different ways. V equals RI is how I write it. It has a symbol like this. Okay? We're going to say this is this, this is this, this is our current flow like that. Okay? And a resistor is the simplest, probably the simplest electrical element you can have. Okay? Again, it just relates voltage across the resistor to its own resistance in ohms and current, like that, right? And I'm certain that you've seen that already, okay? But every time we see that element, we have to think, okay, that is an equation. It's not necessarily an explicit differential equation, but it is an equation that relates those two elements, okay? And so we have to be comfortable with that. Now, how about a capacitor? Okay. What's that? The current, we can do it this way. The current is equal to the capacitance times, the derivative of the voltage. Okay. There's other ways to write it, because you can also write this, which is less commonly written, but you can do it as well. Right? You can do that. Both of those are acceptable ways to write it, and it just depends on how you want to set it all up. But current and voltage is related across the capacitor using that clear, well, sometimes they call it an integral differential equation. Basically, they're differential equations, even though the second one's an integral equation. You could classify them as differential equations. An element like that. If we have current flow like that, okay, that's a capacitor. You can think of resistors sort of like dampers, sort of. You can think of capacitors sort of like springs. Okay, capacitors have a lot like spring-like behavior. Okay, resistors have a damping effect. Capacitors have a spring effect. They can store, capacitors store charge, and you could think of storing charge as a somewhat equivalent of a spring storing energy in compression or tension. Okay? And then the last key element is an inductor. Okay, so that's resistor R, capacitor C, inductor L typically, not I, because we'd be confused with current. So then we got V is equal to L di dt. So it's kind of like the opposite, if you think about it, of a capacitor. Okay? And you could also write this, I is equal to 1 over L integral of the voltage dt. Okay? And again, our symbol, I'm sure you've seen these before, nothing new. Looks like this. Okay. Those are the only main elements we need to know. That's good. An inductor has a mass-like behavior. So as I say in mechanical systems, we pretty much deal with spring mass dampers. In electrical systems, we pretty much deal with resistors, capacitors, inductors. And there's a lot of analogies between the two. We could spend like a long time going over the analogies, okay? I'm not going to do that. It's not, but we will spend a little time, and you'll start to see that a lot of the same differential equations, a lot of the same transfer functions, a lot of the same analysis can come from an electrical system. Okay? Some of the same stuff happens on that side. Okay, now, as in mechanical systems, we have certain rules, namely Newton's laws. Okay? In electrical systems, we've got Kirchhoff's laws. All right? And that's the thing we have to use as well. So every time we do a mechanical system, we say we have spring mass dampers, and what do? We say, oh, let's write Newton's second law. All right? And we just go right to that. Well, in electrical systems, we say, well, let's write a current or voltage relationship using Kirchhoff laws. Okay? So we've got Kirchhoff's laws. Not too many places or names have two H's in a row. You know, that's weird. It's like I looked at that the other day and I thought, you know, I never really thought about Kirchhoff has two H's in a row. How many names have two H's in a row? I don't know. So, anyway, that's just my side thought. So, okay. So voltage. Kirchhoff's voltage law. All voltages. I'm trying to simplify this for you folks, okay? Voltages in a loop. We could spend a whole class on this, right? All semester. All voltages in a loop sum to 0. Right? And a loop is just a full rotation around a circuit element. Circuit diagram. Okay? Sum to 0. Okay? And for current, all currents at a node, right, which is just a fancy word for point on the diagram that where things come together, right, sum to 0. Okay? So I'm trying to boil down circuits class into some just simple concepts. Yep, that's how we do it. It's just like what we did in dynamics. So we do statics and dynamics. Electricals do circuits 1, circuits 2. Same stuff. Just comes down to a lot of the same kind of things in a mathematical perspective, at least. Okay? And a lot of the same kind of processes. Now, obviously, they're different in lots of ways. Okay? And the analogy between electrical and mechanical breaks down when you get into the details. All of a sudden, there's things that just don't make sense. Okay, so you can't take it too far. Okay, but we can do some things. So let's do this. I want to talk, and I'm kind of reviewing some things in the book, but I want to give a little bit different perspective on it. So let's take a look at a circuit. Okay, so we set up a circuit. We say, okay, we've got some kind of voltage source, and we can have voltage sources. We can also have current sources. Oops. We're going to have an RL circuit here. Okay. Now, some kind of voltage source here. Okay. And so typically what you'll do when you do this is you'll typically say, okay, how do I start to write a model for something like this? Okay. You'll say, yeah, I'm going to have to assume a certain current direction. You say, oh, you know what, I'm just going to assume, and typically a lot of times, you know, we'll assume like a clockwise direction. You don't have to. Okay. And then what we'll do is we'll write Kirchhoff's voltage law. Okay. And we'll say, okay, I'm going to usually I start with the input, and I'll say I must have some input voltage source, a battery, something, right? It's plugged in, and it's got a transformer, it's DC, right now because that's all we're thinking, and we're just plugging it in and we're going, right? Okay, so we say, how do I sum the voltages around this loop? Well, I start with my voltage, and you can call it input voltage or whatever, which is V, voltage, right? Now this is a switch. I'm assuming that the switch is going to be turned so that it starts, but there's a reason I put that switch in there. The book does not put that switch in there, and I think you kind of miss something when you don't, okay? So I'm saying, okay, yeah, we'll put the switch on, and then now we're going to write out a relationship with the voltage across voltage across an inductor, and typically we'll write that when we go around the inductor, we'll say it's a voltage drop. Okay, so this is the added voltage, but we typically actually write them as voltage drops. Okay, and so this is L di dt. That comes straight from here, right? V equals L di dt. Inductor right there, V equals L di dt. So I'll just write that. And then minus Ri equals 0. Okay? And you see how I did that? I've got the input voltage. That basically brings the voltage up, okay, to the higher voltage here. So this brings the voltage up to the higher voltage, and then it drops down with those two. Okay? That's typically how I do it. Okay? Now, some could argue you're done, and that's fine. I mean, and I could give you a problem, and I could say, give me a differential equation that models this system. That's it. Okay. In fact, the book says, in some places, it says you're done. That was really easy. Okay. Give me a differential equation that models this system, and I could obviously solve that differential equation probably for the current that's flowing in the RL circuit over time. And that's true, okay? I like to take this a step further, okay? Because I'm always thinking, well, that's great and all, but what are we going to do with it, okay? So I want to take it a step further, and I want to actually put this into the Laplace domain, because I'm always thinking, let's take this to the Laplace domain. All right, now, and I know why it didn't do that, but let's think about this. So if I take this differential equation and I put it in Laplace transforms, I could probably write it like this first. I'm first going to write it like this. The input is equal to, I'm going to just put this to the other side, right? I'm going to bring this to the other side so that we can kind of see it better, okay? The input V, and there's the output differential equation that models the current, okay? Now, let me look at the right-hand side of that. The true way in which you do Laplace transform for di dt would really look like this. S times I of s, right? Because a derivative always has an s. Double derivative has two s's, s squared, right? And then really, you would have this, which I usually skip over when I do mechanical systems. I don't talk about initial conditions. But in electrical systems, you might want to talk about that a little bit more, okay? That's truly the way you would model that if you remember your Laplace transforms from, and I sure hope you do. You should, if anything, go back to DiffEq and review Laplace transforms, okay? And you'll see, oh yeah, when I have di dt, it's just Si minus the initial condition, right? Okay? Plus R I, like that, right? Now, the one thing that we have to do is, what about this other side? You could say, well, this is V of S. You're right, it is V of S. But the one thing with electrical systems is when you close a switch, what you're really doing, and I don't know how much you covered this in differential equations or anything like that, but when you close a switch, what you're really doing with the voltage is you're doing something like this. You have no voltage, no voltage, no voltage, switch, like that. You're really doing that with the voltage, where this is V, okay? We call that, this is one of the most basic type of inputs that we can have. We call that a step input, okay? Because that's what we're really doing. Now, we can do step inputs in mechanical systems, okay? We do that all the time, okay? In fact, we kind of do it implicitly, but I'm going to do it more explicitly as we get later on in the course, and we actually do simulations, okay? When we actually do mechanical simulations, we'll have to start thinking, well, what kind of input do I have here? Well, we have a step input, okay? Now, it turns out that a step input has, you don't just, a step input has its own dynamics, you could say, associated with it, and it has its own Laplace transform, okay? So I don't know if they went over this. I doubt they did it in circuits 2. I don't know if they did this in differential equations and talked about step inputs. But if you model a step input in with the Laplace transform, you remember how they set up the Laplace transform with the Laplace integral, and you go over that all, right? If you do that, you actually get a 1 over s. I don't know if you remember that. I don't know. But every time you have a step input, you actually have a 1 over s in the Laplace domain, okay? So when I do that v of s, it's not just v of s. It's really v of s over s, okay, because that's the step input. You say, well, why does that matter? Well, it matters when you actually go to solve the differential equation, okay? Because if you don't put that in there, if you just put in 1, what you're really putting in is the Laplace transform of an impulse, okay? That's really what you're putting in is an impulse, not a step, okay? And so if you're putting in an impulse and not a step, you're going to get different dynamics, right? So anyways, that's a long story short is that you really have that. So if that's the case, and by the way, let's assume this is 0. Let's assume there's no current running through this before I flip the switch, okay? If that's the case, what I really have is this. V of s over s is equal to Ls plus R times I of s. And now my output current, I of s, can be simulated using input voltage divided by S Ls plus R, like this. Now, do you remember from your differential equations course, if I wanted to solve for the time response of that, do you remember what you do? Just wondering, because we'll get into that a little later. But do you remember what you do? Let's say I solved the, I did Laplace, I did all that, I did some algebra, and I got there. And let's say I want to solve for the time response.
You set up a transfer function and then take out Laplace.
The what Laplace?
Laplace. You set up the transfer function.
Yeah.
Over v of s, then you take the Laplace of everything that's on the right side, then it gives you the time domain.
But well, not the Laplace. Not the. We already did the Laplace. What is it? It's not the Laplace I'm taking on the right-hand side. It's the what? There's another word in front of Laplace. Inverse Laplace, right? Yeah, I know that's what you meant. I know. I just wanted you to be explicit. Yeah, that's what you meant. Yeah, inverse Laplace. Yeah.
That's in the vector domain. You got to go to the time domain.
Yeah, that's what I'm saying. Go back to the time domain. How do we do that? Inverse Laplace. Okay. Yeah, inverse Laplace, right? Now, do anybody remember what you have to do to get it to inverse Laplace? Because like that, you don't just take that straight to inverse Laplace.
You gotta break it up.
You got to break it up. Yeah. You got to do partial fraction decomposition.
Oh yeah.
Yeah, remember that? Yeah. So, okay, yeah. So you have to do that to break it up into pieces, and then from there you can then get turned into the time domain. I'm just reminding you, okay? Okay. Don't worry, I'll remind you again later because we'll be doing this later, okay? So, but right now we're just focused on this. Okay. Okay, we can do that. We can create the transfer function. And yes, I'm starting to think about inputs. We're going to look at inputs, unit impulse. We're going to look at step inputs, the unit step. Will we look at anything else? A unit ramp, I suppose. A ramp is just 1 over s squared. So we'll look at some of the basic inputs there. Okay. And your math folks can derive all that stuff, and they'll actually do the Laplace integral. I'm going to try to avoid using the Laplace integral a lot, okay? Because I don't want to mess with it. We already got tables for all that. This is not differential equations, of course. Okay. So anyway, there we go. Now let's take a look at another example. Okay. Well, that's a little bit harder. Same idea here. Okay. Another example. Okay. So let's say we've got an inductor, a resistor, capacitor like this. And so we've got some kind of input voltage. So this is inductor L, resistor R, capacitor C. And now we want to look at the output voltage. Okay? Again, I'm going to draw an arbitrary loop current there, around there. Okay, like that. And now, based upon our definitions, this should be fairly easy. Okay? This should be fairly easy. We usually go to Kirchhoff's voltage law first and try to draw a relationship. Okay? And so we say, okay, the input voltage, we'll just call it EI. Sometimes we call it V, sometimes we call it E. If you want, I'll put a V there. It's the same thing. Okay? Minus, now we're gonna have voltage drops across each one of these, okay? Minus L di dt. Again, you don't have to memorize that. It'll be in your equation sheet. Okay? Minus Ri, because there's a voltage drop across the resistor, and minus 1 over C integral I dt equals 0. Voltage drop across the capacitor. I'll see that. Okay? Now, we can also do the same thing, by the way, on the other one. We can basically do this. We can say the output voltage minus, the only thing that happens with the output voltage is, we're doing the same thing here with this, is that you're dropping across the same capacitor, so it's 1 over C I dt equals 0. Okay? Because you have to look at that side. There's kind of like a loop on the other side, really, too. Okay? So you have that. Okay? Now, this is fine. In fact, the book, I think, and in some cases I'm going to be happy with this in the homework. I'll be explicit. I'll say in the homework, just give me the differential equation. And I'll even say it, give me the integral differential equation. So this is fine, okay? Because some math folks would say that's not really a differential equation because there's integrals in it and you'd have to transform it and all that. Whatever, this is fine. This is good, okay? That's 2 equations, okay? You could create but I want to create the transfer function, okay? And this is where I think doing this using Laplace makes life so much easier, okay? Because here's what I can do, okay? Let me take that first equation, equation 1, equation 2, take that first equation and write it like this and say, you know what? This is going to be e sub I of s equal to, now every one of those negatives, I'm going to bring it over to the other side, right? I'm going to bring it over to the other side. So just don't miss the algebra I'm doing here. I'm just bringing them over to the other side. No big deal, right? So what is this? This is going to be Ls I sub s, right? Plus R I sub s. Okay, and this is the beauty. Now with that integral, what do you think I do with an integral in the Laplace domain? If I take a derivative, look how I did the di dt. I did Ls how do you think I would do the integral I dt in the Laplace domain? Just a guess. 1 over s. 1 over s. Yeah. So this is going to be minus cs like that. I sub s. Yeah. That's nice. Now, that makes life a lot easier. Okay? Yeah.
Why is it so negative?
Oh, it's not. And it's not even equal to 0. I don't know. I was looking at that. No, it's not. It's not. Yeah, put plus. I was bringing it over to the side, trying to do two things at once to save space. Yep. Okay. And now the second one, now your output, same idea. CS. Let me get this one. Okay. You can then, I'll just go cut to the chase. You can then do a transfer function, output over input, and it looks like this. And there's a point to why I'm doing this, and I'll explain in a second. Okay, there's a transfer function that relates my output voltage to my input voltage with an RLC circuit. RLC circuit is pretty much like a spring mass damper circuit. If you go back in your notes and you look at when I did a spring mass damper circuit, it has a form just like that. It's pretty much the same thing. It's the same differential equation. Now, the terms are a little different, L, C, and R. Instead of mass, K, B, right? MKB, it's LRC. But, you know, things are a little bit different, a little reorganized, but the differential equation's the same. It's the same difference here, okay? And that's what's so powerful about the analogy. So I just urge you to look out for that, because I found when I learned that, and I got more into the dynamics and the dynamic analysis, it made me appreciate the circuits more. It made me go, oh, this isn't that hard. It's just the same thing in a different way. Yeah, there are some things that are harder, yes, but the basics, the fundamentals are very simple. Okay, that's good. One more. So we got to take it to one more, and I don't want to take it as far as what your you know, the book could take it. You know, we could spend a whole other week or two with this. I don't think it's worth our time. But I do want to talk a little bit about a little bit more of an advanced circuit. So we're going to talk about this one. Okay. You need to, and this is probably further than, I'm guessing, further than what you go in circuits one. Maybe not. I don't know. I don't know what you do in circuits one. So that's what's hard. Okay. So let's do this circuit. So we got a resistor. We're going to go down here to a capacitor. Like that. Okay. And then we're going to have another resistor, another capacitor. Okay. Here's our output. Here's our input. We're going to call this R1. We're going to call this R2. We're going to call this C1. We're going to call this C2. And I'm going to assume this current I1. I'm going to assume this current I2 is flowing like that around there. So if I1 is flowing in here, and I2 is flowing there, then what is flowing through here? Well, you call it I3 if you want to, but can you express it in terms of I2 and I1?
I2 minus I1.
I2 minus I1? Or is it I1 minus I2? It's that, right? Because remember, what we know about nodes is they all have to, when you have a node like this, and you got I1 coming in, and you got I2 leaving, here we say this is going to be I1 minus I2, such that you know if I1 is equal to I2 plus I1 minus I2, that way you've got I1 equal to I1. So that works. Whatever comes in current-wise has to flow out. It's not like you're going to make current, because you can't make charge from nothing. Because current's just flow of charge. By the way, if you want to further this mechanical analogy, just as a side note, we have the mechanical domain and the electrical domain. We have the electrical domain, we have voltage and current. If you really look at it, voltage is like force in the mechanical. Force creates basically motion, right? And velocity creates the motion of current, essentially, motion of charge, I should say. And current is the voltage creates the flow of charge. That's what I should say, I'm sorry. Voltage creates the flow of charge. Okay, and the flow of charge is current, and that's really like a velocity. I'll call it VEL, just make sure we're not talking about the same thing. I'm getting myself confused. VEL, velocity. Okay? Okay, so that's the mechanical analog. Voltage is like force, because a voltage makes something happen in terms of charge flowing across something. And when charge flows across something, then you can have electrical work. Okay, you can have something happening. Okay, same thing with a force. A mechanical force makes something happen. Okay, it causes velocity. It causes motion. Voltage causes current. Now you might say, well, wouldn't that be force to acceleration? No, because voltage to current is not the same as force to acceleration. It's really force to velocity, okay, if you look at it. Okay, so we can spend a long time on the mechanics. My mind, I really liked it because I could see things mechanical, and when I started applying that to my circuits problems, I started going, okay, I think it's kind of like this, and it helped me understand it. You might be different. Okay, so now we'll take a look at this system again, okay? And I want to write some equations here. I usually use the voltage law, and I go around a loop, okay? So let's take a look at the first loop with I1. It's going to look like this. E of I, okay, E of I minus R1 I1, because it's the first current, okay, minus, now this is going to be C1, and now we're going to say, sorry, 1 over C1, the integral of I1 minus I2 dt equals 0. Right? So I went around that first loop. Now when I go around the second loop, okay, when I go around the second loop, I'm going to write it like this. Minus R2 I2 minus 1 over C2 integral I2 dt. And then I come back to this same point here. Let me mark it in blue. I come back around, and I come back to this same point. But recognize here that I have drawn the current going down, but as I do the loop, I'm going back up. So I can't do negative. I actually have to do positive because I always do negative. But in this case, I have to do it the other way. So I actually have to do plus 1 over C1, and the same thing here, integral I1 minus I2 dt. Okay? And then that's equal to 0. And I've got one more loop there, the back side here, which is my output, minus 1 over C2 integral I2 dt equals 0. So now I've got three equations, three differential equations. Okay? This gets a little messier.
So which way are you going around the third thing?
Oh, yeah, it'd be like, I usually go from high, start with the highest, go this like that. So you can go that way. So I'm still following that same direction of current flow, so it's minus, going down. Just the other way, I had to go up, so I had to go plus. Okay? So there, I've got my three differential equations. And in some cases, again, we're good. We could say, you know what, you wrote it out. That's good. You're not double E's, and I'm not going to expect you to, on a test, I'm not going to make you maybe do as much with an electric circuit as I would with a mechanical system. I'd expect higher aptitude, more ability to take something harder mechanical system and create a model, an electrical system. Okay, but something simple, or in the homework, I could say, sure, you should be able to do this homework. You should be able to figure this out. Okay, now, I want to take this further because, again, I have a point to make. The book doesn't do this, and I think I know why. It's because it's just trying to get you to this point. But to me, getting to this point is kind of unsatisfying because you look at it and go, okay, I guess I'm done. Okay, to me, that's not satisfying. It's like, okay, that's great, but what do we do with it? All right. So what I want to do is I want to take differential. I want to turn this into Laplace transforms, right? So what I'm going to do is in each one of these, on the top one, I'm going to write it like this, EI sub S. So again, I'm bringing this to the other side, and this is going to be R1 I sub S plus 1 over C1S times I1 sub S minus I2 sub S. Okay, like that.
Would the I instead of I1 be I1?
Yeah, maybe be explicit. You're right. Yes. Okay, yeah. So that's one equation. I'm running out of space, but I think I can get these all in because the last one's not too bad. The next one here, now, what I could do, I mean, you could write the second one infinitely different ways. I'll just keep it simple. I was gonna do something. You don't have to. Okay, let's just do it this way. We'll just say it's going to be this. It would be like this. It'd be 1 over C1S I1S minus I2S, like that. Okay. Minus R2 I2S, okay, plus 1 over C2S I2S. Okay, like that, equals 0.
Why is it plus C2S?
Oh, did I do it wrong? Plus, I think I should. Yeah. and that's why in my mind I keep wanting to put pluses because we do that, but it's your Ed's minus. So, yeah, I was gonna redo it all and have them all be pluses by changing. I could have taken this brackets here, I1 minus I2, and changed it into I2 minus I1. Then they would have all been negative. Then I could have brought it all to the other side and made them all plus. But does it matter? No. Okay. So, and then the last one, it's just usually how we do it. And there's reasons for that that have to do with other things that we'll get to. But it doesn't matter. Okay. And this is, the last one is going to be E out of S is equal to 1 over C2S I2S, like that. Okay, and that's the last one here. Okay, so I'm going to cut to the chase since we're running low on time and I'm running low on space, but I can do this. But if I were to put these together, don't you love it? The miracle, we're going to massage and things are going to happen, and yeah. But if I would, it's not that hard. If I were to put these together, here's what I'm going to get, okay? It looks a little messy, but it's not too bad. The output over the input is going to look like this. Pretty long denominator here. R1, C1, R2, C2, S squared plus R1 C1 plus R2 C2 plus R1 C2 S plus 1. Just got that in. Yeah, a little messy. I have a point to make here. Don't worry, I'm not just throwing things at you. There's a point. There's a reason I chose this. Okay, so if you get that down, okay, there's the output over the input. So if I have some kind of input voltage, I can, through this circuit, I can tell you what the output voltage is. Okay, and there is a transfer function that shows up. Great. Now, what do we really have here? What we really have here are two RC circuits. You see it? There's really two RC circuits that are in series together. Okay? We've got one on the left side and one on the right. We've got one that's R1C1 and one that's R2C2. Okay? And there's basically two RC circuits. So, now if you were to have just one RC circuit, if you had one RC circuit, its transfer function would look like this. It would be 1 over R1C1S plus 1. Okay? If you were to have two RC circuits together, if you were to have it like this, RC flowing into RC like that, where this is the input and this is the output, you might think to yourself that all you have to do is multiply those two transfer functions and you would be good to go. But you would be wrong here. This transfer function here is more complicated than simply multiplying these two RCs together. Even though I have two RC circuits, the overall transfer function is more, there's more to it. This is where we get, I'm sure you talked about this in circuits, but this is where we talk about load and loading. So what's happening is that one circuit is loading the other, okay? And we really have two circuits here that interact with each other, and there's additional dynamics in here, okay? There's additional dynamics. If we had separated these two RC circuits, okay, with some kind of like, basically like a high impedance amplifier or something like that, then they would act separately, okay? But we have these are loading each other, so there's an additional dynamics that does not, you don't even see it until you bring the two together, okay? Is there a mechanical analog to this? Yes. Yes, there is, okay? The mechanical analog to this is when you is the reason you have a transmission. Okay, the reason you have a transmission is that when you have mechanical systems come together in gearing, there are certain points that you have better. You can load each other so that you have a better performance, and so essentially, the gears will still work, but you have a better transmission of power through them. Okay, and we'll get to it later. I think we'll get to that and we'll show that. Okay, and we'll show that mechanical analog. The mechanical analog is basically transmissions. Okay, and you could also sort of relate that to a bicycle and having different gears and having a certain point in which we're designed to pedal at, and you change the gears to kind of keep it at that point. Okay, but that's why we have a transmission. While we change gears, is the same idea, essentially, as loading as a loaded circuit. It's more complicated than just the two pieces by itself. There's an interaction between the two. Okay? All right, so next time we'll keep going and do some other stuff with this.